Welcome back. Let's check out some properties of the definite integral. Definite integral b to a. So notice b is in the lower limit, a is the upper limit. Definite integral b to a fx dx is negative definite integral a to b fx dx. In other words, when we interchange the limits, we introduce a negation. This happens because of the width of the rectangle, of each subrectangle. Notice width is given by b minus a over n when b is the upper limit and a is the lower limit. On the other hand, if a were the upper limit and b the lower limit, then width of each subinterval will be upper limit is a minus lower limit is b over n. Now notice a minus b is same as negative b minus a. Therefore, a negative comes up. This negative gets incorporated when I flip. Okay, that's where that negative comes from. On the other hand, here is second property. A to b constant dx is constant times b minus a. This follows from the following instruction. What is the constant function look like? Constant function y equals c looks like this. Definite integral from a to b basically is area between the curve and the x-axis over this interval. But because this is a constant function, what we get is a rectangle. Area of this rectangle is width times height. Height is c, width is b minus a. So, area is b minus a times c or c times b minus a, which is what we claim. What about definite integral a to b of a sum of functions? Definite integral sum of functions is sum of definite integrals. Why does this happen? Remember, definite integral is limit of summations. If you recall, summation splits over addition. Therefore, definite integral splits over addition. Likewise, definite integral a to b of difference of two functions. It is difference of definite integrals. Why does this happen? Again, this happens because of summation. Summation splits differences. Therefore, definite integral also splits differences. Definite integral a to b of a constant time function. The constant comes out. Again, this follows because of summation. Remember, definite integral is limit of summations, and within a summation, if there is a constant, it can jump out. That's all we have said. Now, this is an interesting one. For any c between a and b, definite integral from a to c fx dx plus definite integral c to b fx dx is definite integral a to b fx dx. What does all this mean? Here is the picture. A to b is here. That's my function. Definite integral represents this area. So, area over a to b is equal area over a to c plus area over c to b. That's all we have said here. Area over a to b is area over a to c plus area over c to b when c is between these two numbers. Comparison properties of the integral. If fx is greater equals 0 for x between a and b, then definite integral a to b fx dx is also greater than 0. This is explained using the following illustration. Note my curve is above the x-axis, so it's greater than or equals 0. So the area is all positive. If the curve were to go down, then you would have some negative numbers to deal with. But if your function is thoroughly above, then the area is going to be positive. That's all we are saying. Here is another property. If fx is greater equals gx, then definite integral, so mind you, this must happen over the entire interval a to b, then the definite integral fx dx is greater equals definite integral a to b gx dx. Again, let's use a picture to see. F is greater equals g. So this is the reverse direction, but anyhow, g is higher than f. So the area under G is more than area under F. So whoever is higher, his area will be greater than the area of the lower function. Now suppose fx is between little m and capital M over this interval, then the definite integral a to b fx dx is between m little m times b minus a, capital M times b minus a. Let's understand this using an illustration. Here is your curve y equals fx. It is above little m and below capital M. So the area under the curve is less than or equal area of the big rectangle, but greater than or equal area of the small rectangle. Area of the big rectangle is width times height, there, and area of the small rectangle is width times height, there. So definite integral is between area of these two rectangles. Okay. Let's verify the inequality using all our properties we've seen so far. We want to show that definite integral pi over 6 to pi over 3 of sin x dx is between pi over 12 and root 3 pi over 12. Looks complicated, but it is not. Let's draw the graph of sin x over the interval pi over 6 to pi over 3. Here is pi over 6, here is pi over 3, and this is the curve sin x. Notice how sin x, the minimum height on this interval is half, and the maximum height on this interval is square root 3 over 2. How did we get these values? Well, sine of pi over 6 is half, sine of pi over 3 is square root 3 over 2. So that gives us a starting point. Sin x lives between half and square root 3 over 2. Sin x lives between half and square root 3 over 2 on this interval. On that interval, sin x lives between half and square root 3 over 2. So if I take definite integral of half and sin x and square root 3 over 2, they would fall in such a line. Length of this, notice I have a rectangle here. With the half, I have a rectangle here. With the square root 3, I have another large rectangle here. Either way, I need the width of my rectangle. Width of the rectangle is given by pi over 3 minus pi over 6. That's all I need. Length of that interval is pi over 3 minus pi over 6, which is pi over 6. You may check. Therefore, this definite integral is height, width. Definite integral sign, whereas the right-handmost definite integral is height times width. In other words, pi over 12 is less equals definite integral of sine and less equals root 3 pi over 12, which proves the result. Okay. Let's try one more problem. The following table gives values of a function obtained from an experiment. Use these values to estimate definite integral 3 to 9 fx dx using 3 equal subintervals, using right endpoints, left points and midpoints. Okay, I'm starting at 3, that's my x value, ending at 9. So that's my interval. It has length 6. I'm supposed to use 3 equal subintervals, 3 intervals. So the length of each subinterval would be 2 because you have 6 total length and 3 subintervals. So the 3 subintervals are starting from 3, length 2, 3 to 5, 5 to 7 and 7 to 9. Using right hand points, the right hand point of the first one is 5, second one is 7, third one is 9. My estimated definite integral is width times height. Width, height, width, height. F at 5, negative 0.6. F at 7, 0.9. F at 9, 1.8. Those are the numbers we use for F. Okay, that's your final answer. Now if you were to use the same intervals but left hand points, so now I would get 3, 5 and 7. 3, 5 and 7. Estimated definite integral is width, height, width, height, width, height. Height now is given by 3, 5, 7. 3, 5, 7. Negative 3.4, negative 0.6 and positive 0.9. Negative 3.4, negative 0.6, positive 0. So that is what we use to calculate using left endpoints. The last example here with midpoints. Now notice midpoints of my intervals. What is the midpoint from 3 to 5? 4. Midpoint from 5 to 7, 6. Midpoint from 7 to 9, 8. So 4, 6, 8 are my intervals. So I'm using appropriately f at 4, f at 6, f at 8 for the height, and the 2 continues to be my width. F at 4, negative 2.1, f at 6, 0.3, f at 8, 1.4, which gets me the final answer. Okay, so let's continue to the next problem in our next video.